Alright, my name is Keith Conley, and I'm right here with an SoC FPGA, specifically the DE1 board from Jurassic, and I'm going to show you this project I put together. I'm actually going to go through the whole how to write the project, since it's a pretty simple project altogether. I'm just going to go through more of the system integration part of it. The whole concept of this project is to create a module in verilog, and that's this module right here, to convert from 4-bit binary into a 7-segment display. Now, the trick is going to be to write to the verilog module from inside embedded Linux inside of an hard processor system. So you can see right here I have a verilog module written to convert binary into a 7-segment display right there, so I'll then test it. And we can see here, this is where I go through and declare all the ports, all the outputs, all the inputs, everything, and call in the SoC system that I'm about to create inside of Qsys, and that we connect it to it. This is actually written using the Golden Hardware Reference Design as a base. You can find that within the documentation very easily. Alright, so how would you actually start about doing this? Obviously, you'd write the verilog module first, and then you just have to figure out how you're going to communicate with it. Then after to do that, you go into Qsys. And it's loading, and initializing. Now, a lot of this stuff will be there already if you're using the GHRD as a reference point. You can also start completely from scratch, but I don't really recommend it, because especially like these development boards, you have to take into account a lot of things like board skew, which those values have already been figured out and put into designs for you if you're using GHRD. So overall, it's just easier. But say for example you did actually want to create it from scratch, you go down here to project, you'd find the hard processor. There you go, and you would add it into it right here. You can see right here that is already in there, and it's a lot easier to just use GHRD as a reference point, because otherwise you have to go down here and figure out everything yourself. You can go right here and you can figure out, you can change the clocks that are going into it, you can change the output clocks, and you can just set what frequency the hard processor is running at, where it's all right here. You also have to tell it how much RAM it actually has and the actual frequency of the RAM. And this is what I was talking about, like board settings. You go in here, you find out board skews, especially with high-speed designs. Board skews starts to become very important. Anyway, right here in the Qsys, you go through, you connect everything up to it. The way I'm actually, well, okay, here's our processor. You can see there it has a bunch of buses, specifically 3 buses going out into the FPGA project. It has then AXI bus. You can see there H2F, hard processor to FPGA, AXI master. It also has a lightweight AXI, and the difference between the two is that the lightweight AXI is a lot lower latency. And because the verilog module is an actual physical module being created from gates, we want to connect up to the lightweight AXI. And you can see right here I have the system clocks going into it, the JTAG UART, and let's see, here's the on-chip memory. You're going to need that as well. So you can set up for the hard processor, use the on-chip memory for resets and all that fun stuff. Now the way I actually decided to communicate with the verilog module is with PIOs, parallel input output. You can essentially think of this as GPIO pins on a microprocessor like an Arduino board or something along those lines. When you go down here, you can see that I set a 4-bit PIO register that has an output. I gave it a reset value, so essentially that on the bus has various addresses. I can write a value to this address to reset the whole PIO. And you can see down here where, let's see, here's a clock. The clock, of course, is going from clock 0, because that's going to be the master clock that this whole thing runs off of. The reset, of course, set to the master reset. And here's the S1 where that's connected all the way up to the lightweight Qsys master. You can see right here when you hover over these nodes, you can see what it's connected to. And essentially the way this whole interface works is that you just click things and you'll connect it up to that bus. You can see right here I have an external connection. That's how it's actually going to, well, this whole system gets outputted into a verilog module that can just be connected up to other verilog modules. Like I'll show you in a little bit. Like here's the HDL example. So after I change all of this stuff right here, it'll go through and it'll give you like an example HDL right here. And this works a lot like a class in higher level programming. So you can see right there I'm declaring like system U1 of SoC system. And I connect all these outputs to essentially inputs and outputs declared in the verilog module, similar to a class constructor. Alright, so this whole thing's through. You click generate HDL, you generate all. I'm not actually going to be generating anything because this is a large program and it takes a long time to actually go through and generate anything. Alright, so we go back here to the top level design, the HBS BCD. Of course, you can see all the way up top, just declaring all the inputs, outputs, and again, this has been used from a reference design. So a lot of this is already figured out. Here's the SoC system. You can see myself you can see how I declared everything to each of these inputs and outputs as needed. The only thing that I really had to change for this whole design is this PIO external right here. I connected to the BCD input, which you can see right here I declared the BCD input as a wire, so I can connect it up to the module right here I'm calling into. People used to do higher level programming is probably going to be a bit confused about this whole thing. But as you can see here that I'm using an input right here, but I'm declaring it down here. And the reason for that is that all this code runs in hardware. So it's all 100% parallel. And that makes sense because when you connect that power to a chip, it just goes. It doesn't think about anything. It just moves. Anyway, after you declare all this stuff, you go up here to the pin planner. And you have to figure out where all the pin locations are. You can see the pin locations represented right here in the chip. So I can click like audio back clock or right there, and you'll see it's right here in the actual chip. You can see here all the GPIOs that I didn't actually use because it's not really connected up to anything. It's just kind of there. Alright. So we go through, we compile design, everything else. Again, I've already done this. My whole compile time is like 20 minutes, and you don't want to sit here for 20 minutes while I'm just doing nothing while it's compiling. Alright, I'm going to set object. This is a SEMA5, and you just figure that out by the actual what's on the chip. So we go down here, we want to add a file. And it's usually under output, this SOF file right here. And we set up so it'll configure the actual FPGA right here, not the SoC. Start, program it. Alright, it's all successful. Next thing I want to do is go to the Eclipse and set that up so we can write some code for it. Because even though I programmed it, it's not going to be doing anything because there's no code for anything. Probably like a termite window up and running too. Termite is just a, well, it's a free program that is nothing more than a serial port sniffer. Set it up there. Let me go ahead and reset the hard processor. You can see the whole thing boot. This is embedded Linux right here. And now I wait for the command shell to start up. The program environment built into this into the Qsys software is Arm DS5, which is essentially a plugin for Eclipse. So right here I type in Eclipse, and it starts Arm DS5 Altera Edition. Now I don't actually have the let's see, BC software. Yes, that should be correct. And I don't actually have the licensing file for this because it's like $1,000 and I am a student. See here, just log in as root and go ls. So I can see the NC FPGA programs right here. And there's my program right there, Hex LED, that I'm going to show you the code for in Arm DS5. So this is all very low level C system programming. And you can see here I'm using a bunch of things like hardware lib H, which is part of the Altera embedded design system package. We can go down here, we can see like all the header files, where this is the biggest one right here. It'll show you how it's declared the memory addresses for basically everything I declared. Like you can see there, it'll show the PIO LEDs, the offset, the data width right there. Alright, so let's go and find the actual main function. Yeah, okay, here's main right here. So go through, I define all this stuff. I assign the register span, and I create a void function right there, virtual base, which I'm going to go through here, and I'm actually opening up devmem, which is a driver that's inside Linux, because again, this is all just Linux that's running off of. And the way drivers works is actually pretty interesting. It just goes right here and it treats this devmem as a file. So I'm using like file open that, and it goes down into the actual driver, and it basically calls like a constructor for it, where it'll map the virtual memory. It'll map the memory needed to the memory of the device it's communicating to. So we can go here, we can see that I'm using virtual base equal to memory map, and right here I'm just setting up and mapping the virtual memory to the memory locations on the chip I actually need. And let's see, yes. Right here is where I actually call virtual base again, and I map the PIO LEDs to the Alta lightweight FPGA bridge, which is a big hex number right over, I believe it's in this one. Anyway, it's a number like 0xFF2000, I believe. Right up to a PIO LED base, which you can see that that's the same value that's in Qsys right here. So it's essentially the first item on the bus, so it really doesn't need an offset, but it's still set up like this, so I can change the offset value of this and it'll map it just the same. You know, you can go down here, you can see like it's declaring a loop, and it goes into a loop. It's setting this HTTP LW address to LED mask. So essentially I can write to LED mask a binary value and it'll light up the way I want it to. Microsleep, it's just mapping clock cycles to microseconds. So you can see there that this comment is actually wrong, is actually waiting 1000 microseconds or 1000 milliseconds or just 1 second. And we can see here it's going to a switch statement. So the loop is starting up here where loop counts less than 60, so it's going to be looping roughly 60 times. Now 60 is just an arbitrary value that I just chosen to, because I don't want to loop it infinitely. Although the first try for this was just an infinite loop, just to do it that way. You see on here it goes to LED count and it just writes a binary value. Now the registers are inverted, so I write a 1 to that register, then the pin's going to output a 0. I'm not entirely sure on that one, but in testing that's what I found, so this is all correct. You can see down here just various codes of me playing stuff. And it's printing out the actual LED count number. This is going down here and like unmapping everything. Anyway, so let's run the actual program. It's very simple. All I do is I do it like that. And you can see here how it's counting. And I'll take out a camera and actually show you the device physically counting in a second. It's all pretty cool. Anyway, you can see right there it's incrementing in 1 second intervals. And it's working exactly the way I want it to. Now I could change the rest of these and set the other LEDs to not display anything. Let's see, I believe that's everything. Yes, the program's actually ended. I'm going to go ahead and I'm just going to run the program one more time so you can see it goes straight from the start. See, it starts right there. It goes 5, 6, 7, 8, 9, and it just loops. Alright. Well, anyway, that's it for today. The main reason I'm actually making this entire video is because when I first started getting started with SoC projects, there wasn't very much at all documentation for it. It was very hectic. Took quite a few months of actually going through and figuring out everything, because I didn't really have the background of the little program knowledge needed to get everything to figure out what I need to and how it all worked. So it was quite a journey, really. Now, the way you actually go through, you'll compile this and you'll get a program right there. And the way you actually get that program onto the device is, well, you can log into it if you have a, there's a Ethernet port on the actual board. You can log into it, and Linux will go through and request a IP address from your server, and you can just connect it through the IP address. So you can actually go through and edit it as an XML file to give it a static IP. And while I'm there, I might as well go through and like map the FPGA connection to it, so it'll actually call up U-boot and it'll configure the FPGA as soon as I press the button and it starts up and everything. But I wasn't really planning on doing that because it was such a small project. The other easier way of doing it is the whole Linux image is set on a micro SD card. So you pop the micro SD card out, you put it into a Linux machine, and you just mount the Linux partition. And you go through and you just drag the file in there, and of course you go through, you right click and give it permission so it can execute the file. I'm not going to go through that part because it's literally just plug it into a computer and dragging and dropping, and it's really easy to figure out. Anyway, that's all for today. Thank you, and I guess I'll make another video next time.